All right. Our third speaker today, or this afternoon, is going to be Jim Fahrny from Comcast. He's a senior fellow there. He can talk about pretty much anything in the world. He's worked on everything from ballistic missiles to digital rights management to sonar to submarines. Like, I could just say anything, and he's almost certainly worked on it. And today he's going to talk to us about kind of where device authentication is going. And so if everybody can join me in welcoming Jim.
Good afternoon. Are we having fun yet? I am. I just enjoy being here. Seeing new faces, and I won't say old faces, but I'll say familiar faces. Anyway, so I have a philosophy on research, and it's driven by working for a big corporation. And what that is to me, research has to do one of two things. I either need to have a direct output from the dollars that are spent that can be applied to something that either solves a problem or goes into the architecture of some new system or service, or I need to learn a lot from the research that may apply to something in the future. So, and you never know what's going to happen down the road, and sometimes you don't even know whether something's going to apply. But we've been doing research with UConn for 4 years now on PUF technology, and we happen to stumble upon some interesting things that I want to share with you today. And I'm going to talk about this in a generic way, but what can a PUF do? So I'm going to talk a little bit about just briefly what a PUF is. I think probably everybody in here knows what a physically unclonable function is. But what do I get from one? What can I get from it? And then I'm going to talk about threat vectors in a device that doesn't have, a host device that doesn't have a root of trust. And I'm going to just talk about high-level threat vectors. And then the question is, for solving a problem, do I have an SRAM PUF? Do I use an SRAM PUF or a ring oscillator? And I'm going to talk about that. The other thing I'm going to talk about is 3 different tiers of using a PUF to solve a root of trust problem. And the bottom tier basically is one where I don't have a security processor core in the device, and then I don't have a key store. The second one, I have a key store, but no security processor. The third one, I stumble upon having a processor that's a security processor and a secure key store that's in that security processor. And then I'm going to talk a little bit about lessons learned and what the other considerations are in doing this. So ring oscillators require at least a few hundred gates, and I'm not saying anything negative. I think we've come a long way in the last 4 or 5 years on ring oscillators and dealing with the ability to stabilize them over temperature, over time. There's a lot that's been done. Ring oscillators are difficult to add into devices or even reconfigure a chip that's already deployed in the field to turn that into turn those ring oscillators to actually create a ring oscillator or several of them for a PUF. But there's always extra SRAM lying around, and there's been development in the SRAM PUF area, and it's usually available in processors, but not always. And you only need to have about 1K to 2K bytes for SRAM PUF now. They've actually shrunk the size down, and then the error correction and the PUF can be downloaded to a host processor or to a security processor if you have one. So for what we're trying to do, we're trying to fix a problem where devices have been deployed, and they've been deployed without a hardware root of trust. And an SRAM PUF can help us in this area. And so, I mean, you can choose either way if you can implement a series of ring oscillators to create a PUF. But in the field, I think that's a challenge, whereas using SRAM and doing an SRAM PUF can actually be something that is truly deployable into a product in the field. So I think this is really fitting. 6 years ago, I dealt with stuff where I was battling to put hardware roots of trust in video devices, which is the bread and butter of cable television. And in other areas, they didn't put hardware roots of trust. And I fought that battle, and I came close to getting fired a few times, but I made it through it, and now they realize, oh, we do need hardware roots of trust. And usually, the devices that, when I don't think about cybersecurity, it's usually too late when I do. I think it just really fits the scenario that we're talking about. So just at a high level, what is a PUF? I'm not going to spend a lot of time on this slide. There's a lot of new technologies, new research that's been done. Like I said, with ring oscillator PUFs, and sometimes both ring oscillator and SRAM PUFs, in error correction and the ability to not have to deal with protecting helper data and things like that with the older style PUFs. So what do I get out of a PUF? I think that's the main point of this slide. I get a non-modifiable identity that's not clonable, and it's unique per device. I get one or more secret keys that are only readable by a security processor if I have one. And then I have a secret key that's used to derive other keys that can be used for authentication, encryption, and code signing. So, threat vectors without a root of trust. Really hard to get this across sometimes, depending on, I saw somebody made a presentation at Cable Labs this year, and it was very unique about, I forget what the exact phrase is, but it's something like technical engineering mismatch with your management and their ability to understand what you're trying to communicate with them. And I have that problem on a daily basis. So anyway, on the threat vectors, there's a lot of threat vectors when you don't have a hardware root of trust, and I'm just scratching the surface, but ones that we deal with in the broadband space and in the video space, MAC cloning, so it's really easy to become someone's MAC address that has active service, and then fake authentication onto a network, easy rootkit installs, ability to attack IP cameras in the IoT space, thermostats, locks, security sensors, and many other things. And then wireless connections can be exploited. Mocha can be exploited, and I can get access to other LAN devices. I can watch everything that's going on a LAN. In addition to that, code downloads exploited, and I can get a device can be turned into a weapon in essence, because it's actually now got attacker code, and they can put whatever they want onto the device. And then I can make a hacker can make a device when there's no root of trust look like any other device in that network, and it can make it even look like a network service. So I'm going to talk a little bit about the bottom tier. This is like, I don't have anything. I just have a processor and some memory. I can install a PUF on a device that has no key store, no security processor. But you have to add something that's called white box crypto. And it's not really crypto, it's more of an obfuscation, but somehow it got the name of white box crypto. There's several products out there. Cryptanium and Cloakware are the two most well-known. There's another company called Arcsan, but I don't think they actually developed a secure key box. The other thing I would say about this is you have to be able to secure the keys, and you have to make the identity non-modifiable. And then, this level is basically curb or knee-high, as we call it. It's not something that can't be broken, but it's something that makes it difficult and creates a bar for a lot of hackers won't go after it. So I have just a picture of it with, whether it's a modem gateway or whether it's a set-top or a video gateway, the pieces that are in there. And basically the white box security is going to do two things. It's going to obfuscate the code when the crypto functions are running, and you can dial that up and down depending on how much of the throughput of the processor you're willing to sacrifice for that. And then the other thing, it's going to secure the keys, and the keys are going to be typically delivered in chunks, not all in one shot, so because they're in a place where they can be extracted, and they go through transforms so that they're not easily determined in that process unless you completely understand the transformation process. So it is actually a pretty decent level of security. The next one is the mid-tier, and mid-tier security, what I would say is I have a place somewhere in the device where I can actually take I have a key box, and I can actually have some place that I can actually put my keys and my identity that a hacker can't get to. But I still need to have white box crypto, the code obfuscation piece, that will allow me to, when the crypto functions or the code signing validation, or any of the encryption, decryption, authentication pieces are run, that they're obfuscated by that white box crypto. So, and I would say this one, based on the analogy, we would call this maybe waist or chest high, depending on the ability to hide those keys and identity and make them not extractable and not discoverable by a hacker. And I have basically the only difference in this is the key store. I have a place to store keys and the identity. And then the top tier, this ends up being a true root of trust, and we're actually doing work on this right now. And you don't need to have the white box crypto. You don't have to pay for that obfuscation of the code. You could add it if you wanted to, but you have a security processor that you kind of stumble upon, and that security processor is somehow enabled but may not have all the firmware to run on it. We just ran across a scenario where we have over 10 million devices and we have a security processor available to us, which is a really nice thing. And so now we can download the PUF and have the PUF generate an identity and as many keys as we want, because we can create derived keys from the first key. And then those keys need to be, transported back up to the cloud so I can do something with that identity and that set of keys for each device because they're unique. So I have to have a way to set up a pre-shared key, or I have to have some way to securely transmit some of this information back up to the cloud. And there's lots of ways you can do it. You could do a Diffie-Hellman key exchange, you could do a number of things, but there's a moment of time here, depending on, we believe we may have a key in there. We're still arguing with the supplier of the chip whether they're going to give us exposure of that key or not. And I don't believe they're being honest with us because they've already sold 10 million of those devices and there's no more money to make unless it's non-recurring engineering. But assuming they don't have a key, there could be a moment in time where when you download this PUF and you extract information, or I put a pre-shared key in the download of the PUF, I have a window of time where a hacker could disassemble and extract maybe a key that I had in the PUF code to actually transport the information back up to the cloud. The other thing you can do once you've done this, you can also include an asymmetric key so that now I can actually lock down the code signing and actually control the code base on the device itself as well, which, if you think about it, it's pretty amazing that there's a scenario where we have 10 million plus devices and we can actually totally lock down this device in the field. It's been deployed for a couple years in many cases. And this is the block diagram of that. So, we have access to a security processor and we're going to load that PUF into that security processor as part of a firmware upgrade. And At least for me, this is kind of exciting stuff, but I am a nerd, so. So there's some lessons learned here, and there's a lot of variations depending on the individual situation, but there are SRAM PUFs out there that are being deployed and mature, and actually we're working with a company. We're a Fortune 50 company, so getting things approved is driven by that a lot, where they sit, and we found a company that's a Philips spinoff, and they actually have a really solid SRAM PUF, and we've actually done a proof of concept, and we're actually looking at doing a trial on this. We can pretty much mitigate almost all of the threat vectors once we add this. We've added one threat vector, and that's the vulnerability moment if we don't have a key in that security processor. But a security processor core gives you an incredible hardware option to actually add a root of trust to a device that was never keyed properly, but was enabled, but may not be running because there's not firmware to have it running. But there's also some other lifting that has to occur. It's not just getting keys. Now I need to have APIs that can access those keys and can use those keys in crypto functions. I also need middleware software or application level software that's going to be able to call into those new APIs and actually do the things that they need to with that. And then the other part is, how do you, 10 million, that's a big number. How do I deploy this in phases? Do I just go for it? I think ideally what you want to do is pick a lot of 100 to 500 units, and you actually do some limited deployment in a friendly environment, and then you actually go through a phased approach to actually do, a few 100,000 at a time, or maybe 500,000, once you've really nailed down all the issues. But it's pretty exciting to be able to have a solution like this and actually see PUF research actually feed into something that becomes real. So I guess at this point, does anyone have questions?
Thanks.
So in a lot of enterprises, well, not in a lot of enterprises, some enterprises, they're looking at either have implemented or are implementing network access control type solutions to meet various government requirements. And right now we're doing some pretty lame things like MAC address and DHCP snooping and those kinds of things to try to identify devices. Do you see this technology making its way into enterprise devices like printers and those kinds of things that typically get pretty subpar authentication?
Definitely. We're looking at that side as well because I don't have to go through the deployment issues on an end device. Yeah.
So does this mean that Comcast is looking at getting rid of bring your own modem and only authenticate modems provided by Comcast? Couldn't help but ask.
No, we can still load that firmware into the modems because we still control the code download to those. Even when you own the device, we still can upgrade the code to them.
So I think this is great stuff, and I really believe hardware roots of trust provide that platform that you can build on. But two questions for you. First of all, key management is always really, really hard. And if you think about key management in this environment and the ability to change keys or be crypto agile, have you thought about that? And then the second piece of it, in the instrumentation, when something like PUFs or other hardware roots of trust mechanisms are used, from an operational standpoint, what's required to manage it long term to get the real trust mechanism that you think you have when you first put it in? So two questions, one about key management and being agile, and the second one, how do you instrument this so that operationally the security you got when you downloaded the PUF is the same security posture that you have, a year later?
Great questions. And Donna, I have a lot of questions I could ask you. At some point, I've meant to sit down with you in the past when you were here, and I've never had a chance to do that. But I used to work as a contractor at NSA and Suite B and all kinds of different things that have happened. But I never got a chance to interface with you, and I need to. So the first question is renewability, and that is a critical issue here, because you're doing something that's going into the field. And so, yes, we have thought about renewability, and we will have mechanisms built into this that we can regenerate the keys that are the derived keys of the root key that the PUF creates. And that will be a renewal cycle, and there will have to be a delivering of those keys in a secure manner back up to the cloud. But yes, renewability on something like this in the field is so essential. And so let me just say one other thing, because I think before I answer the second question, the other thing that's really interesting is the reason we're doing all this is I led a team for 6 or 7 years, and we built the platform called X1, or it's also known as Xfinity. It's got a lot of different names, but it's really the X1 platform. I led the team for that. And it was a pretty high-stress thing, but we built something in that process that I think is really amazing. And what it was is a thing we call field key provisioning system. And so this actual one of these derived keys that will be in this device matches up with what we did on all the video devices in the X1 platform. And what we'll do is we'll be able to build a profile for this device that's never had an identity other than its MAC address. That's why I rely upon it, and change that real easily. But we'll actually have an identity, a 128-bit identity, and we'll have a key. And that key is the authentication key that allows me to authenticate who I am to my profile on the field provisioning system. And now I download anywhere from one or two in the video space, about 9 certificate key pairs in a secure manner off that field key provisioning system. And those keys are the keys that actually allow me to authenticate my device to a customer account. It allows me to do many other things like how do I protect my applications? I need a TLS connection, and that TLS connection is now secured with one of those certificates. So this key that we're talking about is actually the authentication key that allows me to connect with that field key provisioning system, and it's massive. I think we have over 32 million devices now. You can imagine the scale on that. 32 million devices that are video devices that have authenticated and got a download of keys. It was a daunting task to get to that scalability in that issue as well. So yeah, as far as authentication, that's a critical piece of this as well. And so we actually use a symmetric key, believe it or not, for our authentication in that field key system. And it's because of performance. Asymmetric keys are knowingly small, and we could end up being knowingly slow, but we could easily be in a scenario where we could have 70 million devices coming on, and all at the same time something happens and they now want to all get new keys. And so we have to stage that. We can't let them all ask at the same time, but you still want that performance to have those keys be delivered in a very short amount of time relative to customers that are watching television, because that is like an entitlement for many people. Anything else?
We'll take one more.
Sorry, but another kind of two-part question is I may have misinterpreted something. This is kind of starting to hit the same lines as some of the concepts like trusted computing, where we're building it in so that we can trust the hardware platform. And now, would you? And again, this may have been the bit that I missed, but would you expect industry and infrastructure to start being able to trust these same concepts to be able to identify the devices? It's not in the same way it's like, oh, I have a list of MAC addresses, I can say I trust all these people. Would you expect that peoples and providers would start expecting and trusting the same sort of information? It's not just protecting the end users, but could also be leveraged on the other side?
Yes, definitely. And so one thing I would say about that, ideally, if I could take these boxes and roll them back into an environment that I know is safe, then I wouldn't have to deal with that insecure piece of delivering the information over the network to the cloud. I would have them in my environment, and I know I can trust because I have a controlled environment and I'm installing the PUF. So yes, that's the longer term goal, definitely.
Now, which is kind of where I'm trying to get with my question is because it's been tried before, the whole trusted computing platform type stuff, and sometimes when you see applications of it, a lot of providers that end up like creating applications and services that reside within that space, the developers are told like, hey, it's a trusted computing platform, you can do whatever you want. People aren't going to be able to, people can only do X, Y, and Z when they're using this system. But at the end of the day, you have hardware in users' hands, which I don't know. Me being a pessimistic, paranoid security person, I assume like if someone has hardware, it's compromised. We see it like, for instance, in the video gaming space, like very large applications. Companies tell the developers like, hey, it's trusted computing, like you can do whatever you want. Eventually, someone figures out how to pop the firmware on them. They start loading exploited stuff, and now they're running, they're running commands against computers that are just, oh sure, yeah, you definitely, they're just trusting them inherently because it's supposed to be a trusted computing system. And I guess is there like, what do you do to kind of fix that problem of like the whole malicious trusted user, if that makes sense?
So yeah, it's always a challenging paradigm, but I would say also what is, the definition of what trusted computing is. Yeah. Is there some hardware root of trust? Is there code signing? Is there ability to manage, other aspects of the applications that get loaded? Are they signed? That to me, trusted computing is a really broad term. Yeah. It can be. So, if you had like a TPM in there at least, then I would say it's now getting into the realm of trusted. But the trusted computing, I've seen that thrown into even just, I'm signing the main image and that's it.
Yeah. No, definitely. Yeah, no, it's
All
just
right,
like...
sorry,
I'm done.
let's call there. Thanks. Let's thank Jim one more time.